link state routing. So in the previous discussion, we discussed about our distance vector routing, right? But now this link state routing is going to have some different philosophy. We'll see what different philosophy it is going to follow when we are building up the link state routing algorithm. So in this link state routing, each and every node in a given domain here means the complete topology. So each and every node in the given domain maintains the first one, the complete topology of the domain. So if you see, if you compare this link state routing algorithm with the distance vector routing algorithm, in distance vector routing algorithm, every node maintains the information about only its neighborhood nodes. Okay, but now here, if you observe, every node maintains the entire topology of the domain, entire topology, not just neighbors, but it maintains the information about entire topology. Okay, and also they consist of the list of nodes and the links to the list of nodes, and they also maintain how these are connected to each other, that is the type of connection and the cost to reach to that particular connection also. And the third type of information is they also maintain the condition of the link, that is whether the link is up, whether it is working, or the link is down, whether it is not working. Okay, so here the main important thing we are going to use is Dijkstra's algorithm. Okay, so this Dijkstra's algorithm is mainly used for finding the shortest path from a particular node to all the other nodes. So here to build the routing table, all the nodes are going to use the Dijkstra's algorithm, the Dijkstra's shortest path algorithm to build a routing table. Now, if you see here, we have node A, node B, C, D, and E. And every node is connected to some other node with some metric, with some cost, right? So here A is connected to B and C and D. B is connected to A, C, and E. And C is connected to A, B, E, and so on. So if you observe here in the marking, which I am marking right now, this particular node A contains the complete topology. See, now in the link state routing, if you observe the complete topology, this is our complete topology, right? So this complete topology information is maintained by A, and it is maintained by D, and it is maintained by E, and it is also maintained by D. So this is the main difference between the link state routing algorithm and distance vector routing algorithm. Okay, now so if you see here, we have 5 nodes. This domain consists of 5 nodes. Okay. So every node uses the same topology to create a routing table. But the routing table for each and every node is unique. Why? Let us say now, if I wanted to go from Vishakhapatnam to Nagarpolsa. Okay, there may be one person. The city map is same for all the people going from Vishakhapatnam to Nagarpolsa, but the people may be located at different places in Vishakhapatnam, right? So one person may be at MVP colony. Okay, the other person may be at some Pedawal there, and the other person may be at some Adarsh Nagar. Okay, so from that place to reach the destination, they have their unique map, right? Actually, the city map is same, but each and every for each and every person, depending upon the place where they are residing, okay. So every person will have a different route, the different shortest route to reach his or her destination, right? Actually, the route map is same, but basing upon the location of that particular user, the route map will be changing. That is because it will be giving always the shortest distance, right? So for this also, the topology for the complete network for each and every node is same. But how each and every node is going from one that particular node to the other node, the route map is going to differ. Okay, the routing route map here in the sense for the network it is the routing table will be different. Okay, so this is the main thing we have to remember about the link state routing algorithm. Now, so if you see here, obviously the topology must be dynamic because all the time we cannot say that the network will be in up situation, or the network will be always in a working condition. So for each and every node, the node must represent the latest state, okay, of the network. Okay, so not just about the network. I mean, network in the sense it consists of nodes and links. So the latest states of the nodes and links must be advertised for all the other nodes also. So for this reason, the topology must be dynamic. So obviously, if there are any changes in the network, they should be updated for each node, isn't it? So if there is a problem here, okay, so this information should be updated in each and every topology, right? So if you see here, whenever you are coming from Vishakhapatnam to Agropalsa, for every person, let us say this is our route, okay. So Google is going to show some place that this particular is more congested, okay. So whoever the person coming from, that is whoever the person coming to this route, like this route and from this route, it is going to show that here we have a place. So like that, this topology must be updated for each and every node. So now the question is that all the nodes are maintaining the common topology, right? But here the question is how this common topology can be dynamic, and how this common topology can be stored in this dynamic topology can be stored in each node. Okay, because initially none of the nodes know the topology of the network. Okay, only they come to know only they come to know after some time only, isn't it? So in the initial, that is before happening of a change or after happening of the change in the network, initially the nodes do not know the topology of the network. Okay, so for this, to make the nodes to know about the topology, what the link state routing algorithm is going to do, it is going to make an assumption. So what is that assumption? Even though the global knowledge about the topology is not clear, that is, even though the complete knowledge about this network is not clear, now this link state routing algorithm is going to depend upon the partial knowledge. So basing upon the partial knowledge of the network, it tries to convert that partial knowledge into complete knowledge. Okay, so every node knows the state of its link, that is the type of the link, the condition of the link, and the cost to reach that particular link. So finally what we can say, the whole topological information can be compiled from the partial knowledge of the each node. That is, one node, this node will have some partial knowledge of the network, this node will have some partial knowledge of the network, this node will have the partial knowledge of the network. After combining all these things, again every node comes to know the complete topology of the network. Okay, now, so if you see here, the link state knowledge, this diagram represents the knowledge of each and every node. See now, the A state of links. Now, the node A come to know about this particular link, and this particular link, and this particular link. So at the initial stage, at the initial moment of time, A only knows about these three links, and here B only know about these three links, C only know about these two links, D only know about this link, that is which is connected to A. So this is how initially actually it looks like. Now, so if you see here the same thing which we have discussed, A know that it can connect to B with 5 values. So here we are representing the duplicate values here, right? So this is the same value and this is the same value. That is A to B is 5 and B to A is 5. And A to C is 2 and C to A is 2. And A to D is 3 and D to A is 3. So even though there is an overlap in this particular knowledge, why we are maintaining this overlapping information? So this overlapping information is going to guarantee the creation of a common topology. Okay. So because we discussed that, we came to know that each and every node maintains the common topology of the network, isn't it? So this overlapping of this information will lead the nodes to get the common topology and thereby getting the whole domain or whole picture of the network. Okay, so this is the reason we are having the overlapped knowledge in our network. Now, how we are going to build the routing tables now? So here, the routing tables are built based upon 4 actions. What are those 4 actions means? The first thing, creation of the state of the link by each node. called the link state packet LSP. So in the first step, we are going to construct or create, or we are going to know the state of the link from each node. That is, these packets are called link state packets. That is, the packets which say information about the other nodes is called link state packet. So after creating these packets, what we have to do? We have to disseminate these link state packets, right? So we construct the packets and we will not put it with ourselves. I mean, we in the sense the nodes will not put the constructed packets with themselves, right? Because all the nodes must get the complete information about the topology. Obviously, they have to disseminate these link state packets to every other node. So disseminating the constructed LSP packet to every other router is called flooding. Okay, flooding means sending the information through all the interfaces, and that too, it has to be done in an efficient manner and a reliable manner. Now, the third step will be formation of the shortest path tree for each node. So, if you after disseminating LSPs, now what should be done for the packet to go from source to destination? Obviously, we will be looking for optimum cost. So, we are going to find the shortest path tree for each node for the packet to go to the destination minimum amount of time. And after finding the shortest path tree, what we'll do? We will calculate the routing table based upon this shortest path tree. Now the shortest path tree is going to give us some path. So we will build up the routing table basing upon following this particular path. Anyway, in the example, we'll be looking after how these four steps are going to work out. So don't get confused. We'll be clearing everything here. Okay. Now we are going to discuss about the first step, the creation of link state packets LSP. So here, a link state packet carries large amount of information. So what does this large amount of information can contain? We cannot maintain all this large amount of information right now. I mean, for this particular moment of time, let us assume the important information which the link state packet is going to contain. The first one is the identity of the node. The second one is about the list of all the links available with that node. And the third one is the sequence number. And the fourth one is the age. Okay, you will come to know about all this when we discuss about the example. Okay, so these are the four important informations which are maintained by the LSP packet. Okay, so now the LSP packet will be created with this information. So if you see here, the first two values, what are the first two? The node identity and the list of links. What does they specify? They are needed to make the topology. So which node is connected to which node? This node identity and with what cost they have been connected, the list of all the links. So these two informations are needed to make the topology. Okay. Now, the third information. What is the third information? The sequence number. So, what does the sequence number give us? It is going to facilitate the flooding, and it distinguishes the new LSPs from the old LSP. That is, let us say an LSP age is 1 and another LSP age is 2. So, an LSP with age 1 is older when compared to LSP with age 2 because it is just now created, but it is created earlier of this particular packet. So, in order to distinguish between the old LSPs from the new LSPs, we will be maintaining a sequence number, and it also facilitates the flooding also. The fourth information is age. So what is age? It prevents the old LSPs from remaining in the domain for a long time. So there will be a network. So in the network, if we get information at, let us say, 1 hour or 2 hours later, then obviously it will be a problem, right? So for this reason, this age, we use the concept of age to prevent these old LSPs to be we prevent these old LSPs not to be given to the destination. So we'll remove those old LSPs which are remaining in the domain for a longer amount of time. Okay. So why this is needed? I'll say you a small example. Let us say you have done a transaction. Initially at time T1, you have done a transaction which cost 1,000 rupees. Okay. And later at time T2, you have done another transaction for 2,000 rupees. But you did not get message about your transaction T1 about 1,000 rupees. But soon after you do the second transaction, now you got the information about the debiting of 2,000 rupees. but maybe later 1 or 2 days later, again if you get a message that your account has been debited with 1000 rupees. Okay, so then if we have idea or if we remember our transaction that we have done it 2 or 3 days earlier, then it is no problem. But what if we forget about what the transaction what we have done 2 or 3 days earlier? That is the old packet. That this old information is now coming to our mobile. So this would be a problem. We'll be getting into panic state. For this reason, actually the network should prevent these old messages to be delivered to the mobile. So the same reason is in this LSPs also. So to prevent these old LSPs from remaining in our network or in the domain, we have to use the concept of age. Okay. Now, how LSPs are generated? As we have seen in the distance vector routing protocol, there are two types of updates, that is the periodic update and then triggered update. In the link state routing also, the packets are generated on two occasions, when there is a change in the topology of the domain and also on the periodic basis. So this is what we have been discussing, right, when we are discussing from distance vector routing algorithm also. Okay. Now, so finally, actually, for this link state routing algorithm, the periodic updates of LSPs is actually not needed. It is only done to ensure that old information is removed from the domain, because we told that all the complete information about the topology will be there with the every node, right? So at that moment of time, these periodic updates are not needed. But why these periodic updates we are using means to ensure that the old information is not present in the domain. Okay, so here the timer is set for within the range of 60 minutes to 2 hours. So basing upon how we are implementing this link state routing algorithm, the timer is set. Okay, so if we are going to use the longer period, so the longer period, what does it ensure? It ensures that the flooding is not going to occur in the network and it does not create too much traffic. That is, let us say for every 2 minutes we are sending the updates, then the network is completely flooded with all the packets. So that is the reason we are increasing this periodic updates time to 60 minutes or 2 hours. That is only for every 1 hour or for every 2 hours we are going to send the periodic updates if there is no change in the network. Obviously, if there is change in the network, then we have to go for this one. That is, we have to trigger the dissemination of LSP if there is any change in the topology of the domain. Okay. Now, coming to the second part. So first part we have completed, right? In the first part, what we have done? We have generated or we have created the link state packets. Now, what is the second part? The second part is flooding of LSPs. What do you mean by flooding? Flooding means sending all the packets to all the connections from a particular node. Let us say if you take this particular node, okay, this particular node. So how many are connected to this node? This interface and this interface. Sending the packets to all these interfaces. Sending the packets to all these interfaces is called flooding. Okay. Okay, so not just to the neighbors, it is going to send this LSP to all the nodes. Okay, so this process is what you are going to call it as flooding. So after creating the node, what the every node will do? This node sends the copy of LSP out of each interface. So after creating an LSP packet, B sends the packet out of each interface. Okay. Next. Now, the node which receives this LSP packet. Now, let us say B is sending its LSP packet to C. Now, C is receiving the packet from B. Okay. So now if C receives the packet from B, now what does it do? It compares with the copy it is already having. Obviously, C will be having one copy, right? One copy of this entire network. Now, B is sending another copy of the representation of this domain, right? Now, it is sending to C. What C will do? Now, C is going to compare it with its old copy. Okay. Now, if the newly arrived LSP is older than the present one, how we are going to say whether it is older or not? Okay, basing upon the sequence number. Okay, the first thing is first packet sequence number is 1, second packet sequence number is 2, and then 3. So basing upon the sequence number, now C is going to check the packet, the LSP packet which it received from B. So if the packet which is available with C is older than the packet which it received from B, obviously it discards that particular packet. Okay, but if the packet it received is newer, okay, then what it will do? It discards this old LSP packet and then it keeps the new packet. And also what it will do, that is now it keeps the new one, because now C got an updated value, it receives the packet, it keeps this new packet, and what it will do, it sends the copy of this LSP to all the interfaces out there again here. Okay. So, okay, but if you see here, actually C received the packet from B. Now it is again flooding the information to again C to A, C to B, and C to E. So here, what we will do, whenever C receives the packet from D, now C again will not send the same information to B. Okay, so whenever a node gets an information, it disseminates this information to all the interfaces except from the interface through which it received that particular packet. So this is done to stop flooding at some point of time. Okay, at some point of time, C will not send the information to B, and then at another point of time, A will not send information to C, and at some point of time, D will not send information to C. Why? Because D already got the information from A, and again there is no need for D to again send this information to A. The same information, I'm talking about the same information. I'm not talking about the updated information. I'm talking about the same information. So this strategy guarantees that the flooding is going to stop somewhere in the domain. Okay. Now, coming to the third part, very important part. So what is the second part? How we are going to flood the LSV. So in this manner, we are going to flood the LSVs. The third part is formation of the shortest path tree. Now from each and every node, that node or router needs to know the shortest path from that node to all the other nodes. Only then we can optimize the network, right? So for this reason, now we need to find out the shortest path tree. For this shortest path tree, we are going to use Dijkstra's algorithm. So let us now see about this one. So after receiving all the LSVs, every node will have a copy of the whole topology. This we know by now because of our discussion. Okay, but however, this topological information is not sufficient to find the shortest path. So for this reason, the shortest path tree is needed. Merely having the topological information is not sufficient. Okay, so every node must know the shortest path tree from that particular node to the other node. So for this reason, now there is a need for us to find out the shortest path from a particular node to every other node. So this is what we are going to do in this part. Okay, now so what is a tree? We already know by this you came to know about a tree is a graph of nodes and links. Okay, and in the tree, the starting node is called a root node, and for the root node, all the other nodes will be connected, right? So all the other nodes can be reached from this root node only, and that is through single root. Okay. So for each node, now what we require? We require a shortest path tree with that particular node as root. Let us say if we wanted to send information A to B, A to C, and A to D. So we require A as a root node, and from A to B, we should be able to send the information with shortest path. And from A to C, we should be able to send the information with minimum cost. From A to D, we should be able to send the information with minimum cost. Okay. So for each and every node, we require to construct the shortest path tree. Okay. Let us now take an example and we construct the shortest path tree for a particular node. Okay. So in order to find out the shortest path tree, we use a Dijkstra's algorithm. Okay. Now, very important. Please concentrate more. This algorithm now divides the complete nodes, all these nodes in our network into two sets. The first set is tentative set and the second set is permanent set. Okay. So what this algorithm will do, the algorithm will first find the neighbors of the current node. Okay, we'll take an example anyway, don't worry. Okay, so the algorithm, if we take a particular node, that node finds the neighbors of this, let us say if we take A, now it finds the neighbors of all these nodes. Okay, and we make them as tentative. We examine the tentative list with some criteria, and if they pass that criteria, what happens? We make that node as permanent. Okay, what we are going to do, I'm going to repeat again. We take a particular node, okay, we find the neighbors of that particular node, okay, and we make all of them as tentative. Now we implement a criteria for this tentative list. Okay, so if they pass this criteria, then that particular node will be removed from the tentative list and it is moved to the permanent list. Okay, So this is how actually the Dijkstra's algorithm is going to work. Now, if you see, this is the algorithmic representation of Dijkstra's algorithm. So initially we will be starting. So if you see, if you do not understand this algorithm right now, don't get confused. When we see the example, it will be more clear. But I'll try my best to make it more clear. Okay. So initially what we'll do, we will set the root node to the local node and move it to the tentative list. As already we discussed that we have two types of list. One list is tentative list and one list is permanent list. Okay, so first of all what we'll do, we'll set the root node to the local node. So we'll set a particular node, we'll take a particular node, okay, and we move this particular node to the tentative list. Okay, now check here, is the tentative list empty? No, obviously, because this tentative list consists of a root node, right? So this is not empty. So we proceed further in the algorithm. So among the nodes in the tentative list, so among the nodes in the tentative list, that is how many number of nodes are present available in the tentative list? Only the root node is available in the tentative list. Move the one with the shortest path to permanent list, because we are having only one node here, and that will be the obviously the shortest path from that node to the same node. So what we'll do, we'll remove this root node from the temporary list to tentative list to permanent list. So now the root node will be now given to the permanent list. Okay. Now what we'll do, now this root node obviously will be having some neighbors, right? This root node will be having the neighbors. So for each unprocessed neighbor of the last moved node to the tentative list, if not already there, what we are going to do, we have to add each unprocessed neighbor of the last moved node to tentative list. So this is the last moved node to tentative list, right? So now we add the neighbors of this root node to the tentative list now. Okay, so this is how we are going to find out the shortest path. So finally, after completing this tentative list, the tentative list will be empty. So if the tentative list is empty, yes means we will stop the algorithm. Okay, so now we'll see the example first of all, and then we'll be again coming back to this algorithm so that it would be clear for you how this algorithm is going to work. Okay, now, let us now take the example of node A here. Okay, so we shall apply the algorithm to node A. Okay, so this is our node A, right? Now, node A is connected to D, to C, and B. It is directly connected to D, C, and D. So what we'll do to find out the shortest path from A to D, A to C, A to B, and A to E, what we'll do, what we need actually, we need the cumulative cost from the root node to every other node. So we need to find out the shortest path from A to D, A to C, A to B, and A to E. Now this is our aim. Okay, if we consider A, from A to every other node, now we have to find out the shortest possible route. If we consider B, we have to find out the shortest path tree from B to A, B to C, B to D, and B to D and B to E. So like that, for every node, we have to identify the shortest path tree. So now in this example, we are only taking node A. Okay, so we'll take node A, and now we'll analyze the algorithm and we'll find out how this Dijkstra's algorithm is going to find out the shortest path tree for this particular node A. Okay. Now, what are the steps we are going to follow here? So at end of each step, we are going to show some representations. Okay. The permanent circle, which is a circle which is filled. Okay. So this is one representation. And to represent the tentative nodes, we represent the open circle. Okay. And we represent the list with the cumulative cost. Okay. While seeing the diagram, you will understand this. Now, step one. What is our step one? If you see the algorithm, what is our step one? And going back to algorithm, set the root node to the local node and move it to the tentative list. Okay. Now, for our algorithm, what is our root node here we are considering? Now we are considering root node as A, right? So what we do, we are making node A as the root node of the tree, and according to algorithm, after choosing the root node, we have to move it to which list? Tentative list. So we chosen the root node A. I mean, we have chosen the node A as the root node, and we move this root node to the tentative list. So the tentative list will be now updated with A. So from A to A, it is obviously 0. The distance is A to A is obviously 0. Okay, right? And our permanent list is initially empty. Initially, tentative list and permanent list will be empty, but after step 1, now we moved the root node to this tentative list, right? So now the tentative list is containing the root node A with the distance 0. So this is the reason we got set the root node to A and move A to the tentative list. Okay, this is step 1. Now coming to the step 2, what you should do again, we go to the algorithm. What is the step 2? Among the nodes in the tentative list, move the one with the shortest path to the permanent list. So what are the nodes in the tentative list now? Only root node A. So move this node with the shortest path. This is the only node with the shortest path. So remove this node from the tentative list and put it in the permanent list. So for that we are going to do the next thing. If you see, now, the node A is having the shortest cumulative cost from all nodes in the given tentative list. See, the previous tentative list is A with its cost in the bracket. No, so what is algorithm saying? It is saying that remove that particular node and put that in the permanent list. So we are going to move A to the permanent list. Okay. Now A has been moved to the permanent list. Okay. Now what we are going to do? Again, we are going to add all the neighbors of A to the tentative list. Soon after we add A to the permanent list, okay, soon after we add A to the permanent list, immediately we have to add all the neighbors of A to the tentative list. What are the neighbors of A? If you see here, what are the neighbors of A? B, C, and D only, right? So these neighbors of A, B, C, and D must be added to the tentative list. So what is the distance between A and B? It is 5, and A and C it is 2, and A and D it is 3. So the same we have represented here, 5, 2, and 3. Okay. Now we have updated again the tentative list. Now the tentative list consists of B with distance 5, C with distance 2, and D with distance 3. So till now it is clear, right? So we have moved the root node to permanent list, and now we have updated the tentative list with all the neighboring nodes of the root node A. Next, what we are going to do? Now, among the nodes which are in the tentative list, what we have to do now? Find the node which is having the shortest distance. So among this B, C, and D, what is the shortest value? Among 5, 2, and 3, what is the shortest value? C. So now we consider C. Okay. So node G is having the shortest cumulative cost from all nodes in the tentative list. Among all the nodes in the tentative list, this one, C is having the shortest cumulative cost. So what we will do? We again move this C to the permanent list. So finally, now among all D, C, and B, we have C with the shortest cost, shortest cumulative cost, right? So now we move this node C to the permanent list. Okay, now we move C to the permanent list. So if you see here, after moving C to the permanent list, so initially when we moved A to the permanent list, what did we do? We added all the neighbors of A to the tentative list, right? Similarly, when we are moving C to the permanent list, what we have to do? We have to move all the neighbors of C to the tentative list, obviously, right? So the node C is having 3 neighbors. What are the neighbors of C now? A, B, and E, right? But if you observe, A is already processed. So there is no need to touch A now. Okay. But only unprocessed nodes are only node B and node E. Okay. But if you observe, B is in the tentative list with a cumulative cost of 5. Okay. Now, see, if you see here, node A can reach B, okay, through C. That is from A to C and C to B. What is the cost? 2 plus 4, which is 6. But A can also reach B directly, right, which is 5. So since 5 value is less than 6, what we will do? We keep the node B with the cumulative cost 5 in the tentative list. We will not replace. Okay. So do not get confused. Okay. Now A can reach B with 5 and A can reach B along C. Okay. But if A can reach B along C, the distance is 6. But A can directly reach B with distance 5. So we do not remove this particular value from the tentative list. We will put that in the still in the tentative list. Okay. So for this reason, what will be our final list? The permanent list will be A with 0 and C with 2. Okay. Now all the values, all the neighbors of C will be added to tentative list. What are the neighbors of C? A, B, and E. But A is already added in the permanent list, so we not touch. What is B? B with 5. Okay. And D with 3. So C2 tentative list is D with 3 and E with 6. ఇప్పుడు మనము పర్మనెంట్ లిస్ట్ లోకి సి ని యాడ్ చేసాం, అక్కడ వరకు అర్థమైంది కదా. ఓకేనా. సో సి కి నైబర్స్ ఎవరు? సి కి నైబర్స్ ఏ ఉన్నారు, బి ఉన్నారు, సి ఉన్నారు. ఓకే. కానీ ఏని ఆల్రెడీ ప్రాసెస్ చేస్తాం కదా, అది ఆల్రెడీ పర్మనెంట్ లిస్ట్ లోకి వెళ్ళిపోయింది కదా. సో దాని గురించి మనం మాట్లాడలేదు. సో ఇంకెవరి గురించి మాట్లాడాలి? బి గురించి మాట్లాడాలి, ఈ గురించి మాట్లాడాలి. ఓకే. కానీ ఆల్రెడీ బి అనేది కూడా క్యుములేటివ్ లిస్ట్ లో టెంటేటివ్ లిస్ట్ లోనే ఉంది. దాని క్యుములేటివ్ కాస్ట్ ఎంత? 5. అయితే ఇప్పుడు మనం ఈ బిని ఎందుకు బయటకు తీయట్లేదు అంటే, యాక్చువల్ గా ఏ నుంచి బికి వెళ్ళడానికి 5 కాస్ట్ వెళ్తున్నాం. కానీ ఏ నుంచి బికి సి ద్వారా వెళ్తే ఎంత కాస్ట్ తో వెళ్తాము? 6 కాస్ట్ తో వెళ్తాము. అవునా కాదా? సో అందుకని ఇప్పుడు మనం ఏ నుంచి బికి సి ద్వారా వెళ్తే అది షార్టెస్ట్ పాత్ అవుతుందా అవదా? ఏ నుంచి బికి సి ద్వారా వెళ్తే షార్టెస్ట్ పాత్ అవుతుందా అవదా? అవ్వదు కదా. అవ్వదు కదా. సో ఆబ్వియస్ గా అందుకనే బిని మనం తీయట్లేదు బయటికి. మీకు అర్థమైందా? ఇప్పుడు ఒకవేళ ఇక్కడ అలా కాకుండా ఇక్కడ 2 ఉండి ఇక్కడ 1 ఉంది అనుకోండి. ఓకేనా. ఇక్కడ 2 ఉండి ఇక్కడ 1 ఉంది అనుకోండి. ఇప్పుడు ఏ నుంచి బికి వెళ్ళడానికి ఎంత అవుతుంది? వైఆర్సి 3 అవుతుంది. ఇక్కడ ఎంత ఉంది? 5 ఉంది. సో ఇప్పుడు మనం ఏం చేయాలి? ఆబ్వియస్ గా ఇప్పుడు దీన్ని ఈ రూట్ తో రీప్లేస్ చేయాలి. కానీ ఇక్కడ మనకు ఉన్నది 2 and 4 కదా. సో అందుకని దీన్ని మనం రిమూవ్ చేయట్లా. అర్థమైందా మీకు? So because if you see here in our algorithm, add each unprocessed neighbor of the last moved node to the tentative list if not already there. And the next point is very important. If the neighbor's tentative list, if the neighbor is in the tentative list with larger cumulative cost, replace it with the new one. But our neighbor in the cumulative list is not with the larger cumulative cost. It is with the smaller cumulative cost. That is the reason we are not removing this one. Adhamainda? Okay. So finally our permanent list will be A with 0, C with 2, and the tentative list is B 5 and D 3 and E 6. ఈ కాస్ట్ దేనికి? ఏ నుంచి B కి 5. ఓకే. ఏ నుంచి D కి 3, ఏ నుంచి E కి 6. 2 plus 4 6. ఓకే. Now step 4. ఇప్పుడు step 4 లో what we are going to do? Among the tentative list, this is our tentative list. Among the tentative list, which is the shortest value now? D. Okay. So you choose D now. So we'll choose D. Node D is having the shortest cumulative cost among all the other nodes in the tentative list. So what we'll do? We'll remove that and we'll move it to permanent list. So we moved that D with the shortest cost from tentative list and moved it to permanent list. Okay. So if you see D, this is the D, right? What are the neighbors of D? Only A, but A is already processed. So there is no problem. We cannot add any other nodes to this particular tentative list. Now what nodes are available remaining in the tentative list? D with 5 and E with 6. Right. Now step 5. So among this one, which is the shortest cost? B, right? So we remove B. We remove B, and what we'll do? We'll put B in the permanent list. But who are the neighbors of B? Who are the neighbors of B? A, C, and E. But A and C are already processed. Only E is not processed, right? Okay. But from, if you see, A to B and B to E is how much? 5 plus 3 is 8. And if A go through C, A to C and C to E is, it is 6, right? For this reason, what we are going to do, we still put E of 6 in the tentative list only. You got it? If this particular value, let us say if this particular complete value, if it is 2, then we can update this particular value from A to B and B to E. But because here 8 value is greater than 6 value, If the value is greater than that particular value, we will still put the node in the tentative list only. Okay. So finally, what we'll do now? We will take the last node in the tentative list. This is the only last node in the tentative list. Now we will take this node. Okay. So after taking this node, what we will do? E is only the shortest cumulative cost among all the nodes in the tentative list. So what we'll do? We'll move E to the permanent list. And also E is not having any neighbor. In the example, if you see, of course, E are having neighbors, but they are all processed. Okay. So now the tentative list is empty. So what we'll do when the tentative list is empty, we'll stop our algorithm and our shortest path tree is now ready. So the final list is the permanent list is now A. From A to A, we can go with 0. From A to B, the minimum cost is 5. From A to C, it is 2. From A to D, it is 3. And A to E, it is 6. Okay. So this is how we are going to perform, or we are going to construct the shortest path tree from A to all the other nodes. We are not going to construct not just for A. We have to construct the shortest path tree from B to all the other nodes, and then C to all the other nodes, and from D to all the other nodes. So like this, for every node, we will construct the shortest path tree using this Dijkstra's algorithm. Okay. So finally, if you see here, the final point in linked state routing is we have to calculate the routing table from the shortest path tree. Okay, so if you see here, we are going to calculate the routing table. Node A to A cost 0, A to B 5, A to C D, A to D, A to C 2, A to D 3, A to E 6. But the next router is here C. We are going through C, and now A is directly connected to all these other nodes, because that is the reason we do not maintain any next router information. But A can go to E only via C. Okay, so this is how we are going to construct the routing table for node A. Similarly, we will construct the routing table for node B, node C, node D, and node E, and all these values will be disseminated periodically. Okay, so this is how we are going to perform the linked state routing algorithm, and mainly we will be finding out the shortest path between every node. Okay, so this is a glimpse of all the steps what we have done right now in our algorithm. This is the complete topology. Okay, so initially we moved the root node A to the tentative list, and then we found out all the neighbors of the root node A, and then what did we do? We moved root node A to the permanent list, and among all the tentative list values, what did we do? We find out the shortest value. This is C. And now we again find out all the neighbors of C. What are the neighbors of C? A, B, and E. As already A is processed, now we are only left with B and E. So now C is moved to permanent list. So C here is moved to permanent list. Okay. So now after moving this to permanent list, what we have considered? Now we have considered D. Okay, because that is the shortest path in the that is the shortest distance in the tentative list. Now after finding out D, we move D to the permanent list, and then finally we moved B to the permanent list, and then at the last we moved E to the permanent list. So if you observe here, I'm going to remove this eraser. So if you observe here, this is the original topology. Now when you come here, this is the shortest path from A to every other node. Have you found out the difference here? Okay, if you see here, this particular link has been removed. Okay, shortest path tree, because this particular link, there is no need for A to go via C. Okay, that is A to B it can go. Okay, A to C, and from C to E, and A to D. There is no need for A to reach B via C, because obviously this value is the shortest value. Okay, the smallest value. Okay, so this is our final tree. Okay, so which tells the shortest path from root node A to every other node. So likewise for B, C, D, and E, we are going to find out the shortest path tree using Dijkstra's algorithm, and then finally we find out the routing table for each and every node like this. Okay, and then these routing tables will be now disseminated for each and every other node, so that every other node now gets the complete information about the nodes in the given network. Okay, so this is all about the linked state routing algorithm.